Section 5-7 is on the definite integral properties. The objective of this section is to evaluate definite integrals using the fundamental theorem of calculus and using your definite integral properties, which we're going to talk about here in a minute. If you recall, we've already covered the properties of limits way back in Chapter 2. We've talked about all those properties. We talked about all the properties for derivatives, and we've talked about all the properties for indefinite integrals. And so now it's time for us to cover the properties of definite integrals now that we know the fundamental theorem of calculus. All right, the first thing we need to talk about is the notation that we're going to use from this point forward for definite integrals. You saw with the fundamental theorem of calculus that we defined a function g of x, which was our antiderivative, and then you evaluated that at the lower bound, you evaluated it at the upper bound, you took the difference of those two. We're going to kind of try to condense all that a little bit, and so it's going to look something like this. We're going to still say that g of x here is our antiderivative of f of x dx, but I'm not going to write that down separately. I'm not going to write down that g of x is equal to whatever the antiderivative of. I'm just going to simply use that here for the name of my antiderivative as I show you this. And right here is exactly how we're going to kind of come up with a shorter notation for finding a definite integral. So if you have the definite integral from a to b of f of x dx, the way that you're going to evaluate this is you're going to find your antiderivative, which is what we call g of x, and we're just going to write that down. I don't need to say g of x equals anything, just simply write down the antiderivative. And then we're going to use this little vertical bar here with the a and the b on there to indicate that I need to take g of x and evaluate it at b, evaluate it at a, and take the difference. That's what that vertical bar with those two numbers on it means. Take and evaluate that function at 2 points and take the difference between them. And so you can see that's how we end up with g of b minus g of a. That's what that notation means. So that's going to be kind of our shortcut here, our shorthand for this definite integral notation. Let's take a look at an example to help illustrate that. All right, so let's say that we have this definite integral from 1 to 4 of x squared dx. So using the notation that we just talked about, again, I'm not going to say g of x equals and then write down its antiderivative. Instead, I'm just going to write down the antiderivative of my function here. Antiderivative of x squared is 1/3 x cubed. Just use your power rule, of course. And what you saw with the problems that you did with fundamental theorem of calculus is when we found the antiderivative, of course, we always had a plus c at the end of it. But in the process of evaluating that antiderivative at the upper bound and then the lower bound and taking the difference, the plus c's actually ended up canceling each other out. And that's going to happen every single time we're working with a definite integral. So for that reason, we're not going to worry about writing the plus c down when we're dealing with definite integrals, and only definite integrals. If it's indefinite integrals that you're working with, you have to put the plus c. So I'm not going to worry about in this problem here putting the plus c because I know it's going to end up just canceling itself out. And I put my vertical bar, that's our new notation, and I put the 1 and the 4 to indicate I'm going to plug in 4, plug in 1, and then take the difference. So this turns out to be equal to 1/3 times 4 cubed minus 1/3 times 1 cubed. Again, that's what that vertical bar means. Plug in the upper bound, the 4, and then plug in the lower bound, the 1, and take the difference in those two. So we end up with 4 cubed is 64/3 minus 1/3, 64/3 minus 1/3. I guess I can write it that way for us. Would be 63/3, and that's actually 21. Okay, so this is our new notation that we're going to use right here for evaluating definite integrals. Find the antiderivative. Don't worry about the plus c. Put that vertical bar there with the 1 and the 4 to indicate the upper and lower bounds, and then finally evaluate that. All right, let's take a look at some of the properties here that they give us. There's 6 properties actually in all. And so let's go through each of these 6, and we'll give a little explanation or example to help illustrate why that property is what they've given us. So the first one here is for positive and negative integrands. The integrand, remember, is the function you're integrating. So the first part of this one says if f of x is greater than 0, so f of x is our integrand, our function. If that function is greater than 0, in other words, it's always above the x-axis, it's always positive, for all x in the closed interval from a to b. Then the definite integral from a to b of f of x dx is also positive. It's also greater than 0. So if your function is greater than 0, your definite integral will be greater than 0. The second one says if f of x is less than 0 for all x in the interval from a to b, so if your function is below the x-axis, then the definite integral from a to b of f of x dx is going to be less than 0. This is why we say that the definite integral is the signed area. We say signed because of the fact that it could be positive or negative. Area, of course, is always positive, but we say signed area, meaning it could be a positive or negative value that we get. Here's exactly the reason why it turns out to be positive or negative, depending on your function, whether it's above or below the x-axis. So let me draw you a sketch to help illustrate this for you. And actually, let's first remind ourselves of what a definite integral is. Definite integral from a to b of f of x dx. Remember, we define that as a limit as n goes to infinity of a Riemann sum, r sub n. And of course, a Riemann sum, this is the limit as n goes to infinity. A Riemann sum is just a sum. It's called a Riemann sum because it's a sum of your function values times your delta x values. So that would be the sum from k equals 1 to n of your function at some sample point times delta x. That's how we calculate a Riemann sum. You take your function value at a sample point and then multiply by delta x, and you add all those guys up. So let's illustrate this here with a couple of graphs, why we end up with a positive or a negative definite integral. Let's start out with the positive part. Let's just draw some function here. It really doesn't matter what our graph looks like as long as it's positive on the interval from a to b. So let's say this is a and b. And let's split this up into subintervals here so I can illustrate the Riemann sum. The Riemann sum says, of course, that you are calculating the area of each rectangle here, and I'll just pick heights for my rectangles. I won't worry about exactly where they're at, but we'll just pick heights for our rectangles in each subinterval. And you end up adding all these guys up, taking the limit as n goes to infinity, and that's approaching your definite integral. But you can see here that because my function is above the x-axis, that means that f of x is greater than 0. And you can also see, since I'm integrating from a to b, when I calculate delta x, when I do take b minus a divided by n, delta x is going to be greater than 0. So in other words, I have two positive numbers here that I'm multiplying together. My function values are positive and my delta x values are positive. And so because of that fact, it turns out that the sum is going to be a positive result. When I multiply these two positive numbers, I get a positive result. On the other hand, let's graph a function that's negative. So again, it doesn't really matter what my function looks like as long as it's below the x-axis here from a to b. And let's again split this up into some subintervals. And we can even sketch in what our rectangles will look like here. Again, I'm not going to be too picky on the heights that I pick, but we'll just simply sketch in our rectangles like this. And so that right there is our Riemann sum that we'd be calculating. But now you can see, because my function is below the x-axis, that is that f of x is less than 0. But as I go from a to b, when I calculate a minus b, that b minus a divided by n, that's the delta x. The delta x is still going to be positive. So I have my function value is negative, but my delta x value is positive. So the product here now becomes a negative number. A negative times a positive gives me a negative result. Thus the reason my definite integral turns out to be negative. Okay? All right, take a look at the second property. The second property is for the reversal of limits of integration. So it says there that if you integrate or find the definite integral from b to a, you're starting at b and going back to a, in other words, if b is greater than a, of f of x dx, that turns out to be the opposite of the integral from a to b of f of x dx. So in other words, if I switch the limits of integration, swap the a and the b, you end up with the opposite of the opposite definite integral. All right, so let's see if we can explain why that's the case. And actually, there's a couple ways that you could explain this. I'm going to use the similar explanation that we just did in the last one there, where we defined what a definite integral was in terms of a Riemann sum. In fact, I'll go ahead and rewrite that for us. It's the integral from a to b of f of x dx. That's the limit as n goes to infinity of the sum from k equals 1 to n of your function value at your sample point times delta x. That's my Riemann sum. And the key there this time is not going to be the function value like in the last property. It was looking at the f of c sub k values, whether they were positive or negative. But now it's the delta x value is really what it comes down to, is what's going to determine the sign for this thing. But remember that if b is greater than a, which for most, greater than a, which for most problems, that's how we set these up, that b is greater than a. Of course, it doesn't have to be that way, but usually that's the way it is. But if b is greater than a, then that means that b minus a is going to be positive. If you have a bigger number minus a smaller number, then you get a positive result. And not only that, but delta x, which of course is equal to b minus a, we just said that's a positive number, divided by n, that's a positive number, that's got to be a positive result. So delta x is greater than 0. And so in that case, since delta x is greater than 0, when we multiply f of c sub k times delta x up here, we're going to be multiplying our function values by a positive result, or by a positive delta x. So we get potentially a positive result. Now on the other hand, if b is greater than a, oops, but we're going to start out at b and go back to a, then that means that a minus b is going to be less than 0. If b is greater than a, then you take the smaller number minus the bigger number, you get the opposite result. A minus b must be negative, which of course means that when we calculate delta x from b to a, you take a minus b, which we just said was negative, and divide it by n, which is a positive number. This turns out to be less than 0. And so in that case, since your delta x is negative, the only thing that changes in this problem is if I switch the endpoints from a to b versus b to a, these delta x values go from positive numbers to negative numbers, and thus the sign of my definite integral changes from positive to negative, or negative to positive, whatever it was to start off with. All right? Take a look at the third property here. This is for the sum of integrals with the same integrand. That is where the integrand is your function you're integrating. So here we have the definite integral from a to b of f of x dx. And it turns out that that's equal to the definite integral from a to c of f of x dx plus the definite integral from c to b of f of x dx. Now, if you think about when you first started learning how to find area, you had nice figures. This is back in elementary school. You had some nice figures that you're working with, but eventually they weren't so nice figures. And so one method that you learned to find the area of it was to split that region up into some nicer regions to work with. Like you might split it up into a triangle and a rectangle, and then find the area of each individual part and add those pieces together. And that's really what we have going on here. In other words, let me illustrate that for you, that if you had this region that maybe looks something like this, and of course it's a trapezoid, so we could find the area using our trapezoid formula, but if you didn't know your trapezoid formula, you could say, well, here I have a rectangle, and here I have a triangle, so I could find the area of those two individual pieces. That is, I could find the area of the two pieces, add those together, and it gives me the area of the entire region which turns out to be this trapezoidal shape. That's this guy here. So this is nothing new for us. It's just telling us that we can add pieces of area together and get the two pieces add up to give us the whole. But in terms of a function now, let's just illustrate that with a graph here. If I take a function, again, it doesn't really matter what my function looks like, but if I have some function here that goes like this, we'll say from A to B, we'll say this is A, and we'll say that this is B. So if you want to find the definite integral from A to B, that's of course finding the area of this entire region right here. You can of course find the area of the whole thing, and that's going to give you from A to B, and that's going to give you that region. Or you could split this up, and I could find some point. I'll just pick a point here. We'll say that this is C. I could instead integrate from A to C and find the area of this region, and then integrate from C to B. That is this region. Add up the two pieces and get the whole. Same thing with our trapezoid example that we had up above. Okay, and that's all this is saying. The definite integral from A to B is the same as the definite integral from A to C plus the definite integral from C to B. In fact, C does not even have to, let me just illustrate this with a sketch. C does not even have to fall in between A and B. I could sketch a graph. Call this f of x again. This could be A, this could be B, and C could be either before or after the interval from A to B. It could either be before A or after B, like I've got it sketched here, and the same is still true. If I want to find the definite integral from A to B, this guy right here, then one way to do that would be to find the integral from A to C. That's this whole region. And then find the integral from C to B, and that's the key, is you got to go from C to B. Notice that to do that, I got to go backwards, and that's in essence going to give me the opposite of this region, which means it's subtracting that area off, and that's why you end up with the green region we sketched in the first at the beginning. Okay. All right. Take a look at the next property. This is the property for the integral between symmetric limits. And when we say symmetric limits, we're talking symmetric around x equals 0. So we're integrating from -5 to 5, or -10 to 10. Or we wrote it as here, -a to a. That's the symmetric limits we're talking about, symmetric around x equals 0. So it says here, if f of x is an odd function, we'll have to remind ourselves here in a second what an odd function is. But if f of x has the property of being an odd function, then the definite integral from -a to +a of f of x dx turns out to be 0. That turns out to be real easy to integrate. It's always 0. The second one says if f of x is an even function, then the definite integral from -a to a of f of x dx is equal to twice the integral from 0 to a of f of x dx. Okay? Let's first remind ourselves here of what it means to be odd and even. We might, if you remember that, that's great, but if you don't, let's give ourselves this reminder here. First of all, if your function is odd, let's start out with that one. If f of x is odd, then f of -x is equal to the opposite of f of x. This is our property for being odd. All right, that says f of -x is a horizontal reflection of your function, and the opposite of f of x on the other side of that is a vertical reflection of your function. So in other words, if you do a horizontal reflection of your function and a vertical reflection of your function, and you end up with what you started with, you must have a function that's odd. Another way to look at that is this means that you have point symmetry about the origin. Remember, point symmetry means that it has a rotational symmetry of 180 degrees. So if you take your graph, spin it 180 degrees about the origin, and you end up with the same graph you started with, you got yourself an odd function. All right, let's take a look at even then. That might help to refresh your memory as to what even is now that you know what odd is, but let's still write this down. If f of x is even, then f of -x is equal to f of x. And so this says if you take into a f of negative x is a horizontal reflection of your function reflected across the y-axis, and it turns out to be the same as the function you started with, f of x, you got yourself an even function. Another way to think of that is that's line symmetry over the y-axis. Okay, so if you can reflect it across the y-axis and you get the same graph that you started with, you got yourself an even function. Okay, so we're talking about these two types of functions. So let me just go back up there and remind ourselves of what we're saying the property is. If f of x is odd, then the definite integral from negative a to a of f of x dx is 0. If it's even, then the definite integral from negative a to a of f of x dx is twice the definite integral from 0 to a of f of x dx. So let's see if we can show that here with a couple of examples of odd and even functions. So let's start out with, let's do the odd function since that's the first one in there, and that's actually the nicer of the two because of the fact that it ends up being 0. So if we have a function that's odd, so let's sketch a graph that has point symmetry about the origin. So we'll sketch a graph that looks maybe something like this. Remember what it means there is I have to be able to spin this 180 degrees and end up with the same graph that I started with. So that looks like it has kind of that property. And let's indicate our values of our endpoints here. Let's say that this is negative a, and let's say that this is positive a over here. Those are symmetric, or supposed to be. Realize what we're doing when we integrate from negative a to a, we're taking this area right here, that region, which since it's below the x-axis, it must be negative. The definite integral is negative. And we're combining that with the area of this region, which again, since that's above the x-axis, that must be positive. And since it's an odd function, those are exactly the same amount of area. One's positive, one's negative, so the sum is 0. Okay, that one's really nice. Take a look at an even function. And let's just sketch a graph here that is positive. You could sketch one that's positive or negative, but I'll just do one that's positive here. That's got to be even. And let me try that again here. In fact, let me just start with the curve, and then we'll put in our x-axis or our y-axis to make it an even function. So let's say it looks something like that. It's a little bit closer to an even function. Again, there's got to be symmetry across the y-axis, so I'm not quite symmetric, but you get the idea. We'll call this negative a, and we'll say that this is positive a, somewhere about right here. And since we're above the x-axis, again, the definite integral from negative a to a is actually finding the area of this entire region right here. Okay. But because there's symmetry, the region over here on the left side, this region right here, is the same as the region over here on the right side, this region right here. Those are exactly the same because of the fact that it's an even function. So what I could do is just simply find the area of this green section over here and double it, and I'll get the area of the entire thing. So if I integrate from 0 to a and double that answer, that turns out to be the integral from negative a to a. That's our odd and even property. For symmetric limits, the key is it's got to be symmetric limits that you're working with. All right. The next property, there's actually two of them here. These look very similar to properties you've seen for limits, derivatives, and indefinite integrals. And actually, it's basically the same property here that we have for definite integrals. This is the integral of a sum of functions. So if we have the definite integral from a to b of f of x plus g of x dx. So it's the sum of function f and g. Turns out that's equal to the definite integral of f of x dx plus the definite integral from a to b of g of x dx. So the definite integral of a sum is equal to the sum of the definite integrals. We use that same terminology, that same verbiage there when we described limits, derivatives, and indefinite integrals for the same property. So it turns out all four of our calculus techniques here use this exact same property, basically. All right, the other one is the integral of a constant times a function. And it turns out that the definite integral of from a to b of k times f of x dx, where k, of course, is this constant, is equal to the constant times the definite integral from a to b of f of x dx. So just like with limits, derivatives, and indefinite integrals, turns out definite integrals here have the same property. The definite integral of a constant times a function is equal to the constant times the definite integral of the function. All right. And finally, the last property that they give us is for upper bounds for integrals. And it says here if function f of x is less than g of x. So if you look at the two graphs, and function g of x is always above function f of x. For all x in the interval from a to b, the closed interval from a to b, then it turns out that the definite integral from a to b of f of x dx is also less than the definite integral of g of x dx. All right. This isn't one that we use very often, but it does tell us something about the definite integral in terms of what its bounds are. I can either set an upper bound or a lower bound in this manner. And let me just draw a sketch here to help illustrate why this is the case. So I have two functions, f of x and g of x. And so we'll sketch those two here. Let's say that this is function f of x. And for ours, we were saying that f of x was always less than g of x. So I got to sketch g of x above this, and you can put whatever kind of curve you want on g of x. In fact, they could even be below the x-axis, as long as f of x is always below g of x. And let's say that this is the interval here from a to b. And so the conclusion of this one says that the integral from a to b of f of x is less than the integral from a to b of g of x. And so if we just kind of mark these two, you'll see that if we're finding the definite integral from a to b of f of x, we're finding the area of that region. And you'll notice that that's completely enclosed in the definite integral from a to b of g of x, here, which is this region in blue. So you can definitely tell here that f of x is definitely has a smaller definite integral than g of x because of the fact that it's completely enclosed within the region for the definite integral of g. All right. And that is the end of this section here for us.